Researchers found a way to solidify the ground beneath your feet. No cement, no heat, no machinery, just an enzyme from a bean. And it actually works. That should not be possible. Ground stabilization is one of the most expensive, carbon-intensive, technically demanding problems in civil engineering. Cities have been built around it, avoided it, or thrown billions of dollars at it for over a century. Not in theory, not in a simulation. In the field. In real sand. With real grouting equipment and an enzyme extracted on site using nothing more than tap water. 3 days later, the ground was 3 times stronger. That result is sitting in a peer-reviewed journal published by the American Society of Civil Engineers. It has been replicated. It has been verified. And it is not being used at scale anywhere on Earth. That gap between what this technology can do and where it actually is what this video is about. Because the places that need it most are not abstract. Tokyo, San Francisco, Istanbul, Jakarta. Mexico City. Cities where entire districts are built on ground that will liquefy in a major earthquake. Not might, will. Engineers have mapped it, they have modelled it. They can point to specific neighbourhoods and say, when the shaking starts, this fails. Millions of people living and working on ground that behaves like solid earth. Until it does not. It happens in seconds. A building that was standing is now tilting. A road that was passable is now split. A water system that served 1 million people is now gone. Not damaged. Gone. We have known this was coming for decades. We now have something that can stop it, and we are not using it. To understand why, you first have to understand what actually happens when the ground gives way, because it does not do what you think it does. What looks like solid ground, it isn't solid at all, it's a structure. Imagine millions of grains, each one irregular, angular, pressed against its neighbours. Force travels through that network, grain by grain. Every step you take, every vehicle that crosses a road, every building that rests on that ground, all of that load is being transferred through tiny contact points between particles. No chemical bonds, no glue, just friction and geometry. That works, until water gets involved. In saturated soil, where all the spaces between grains are filled with water, something dangerous can happen when the ground shakes. The shaking tries to compress the soil. The grains want to pack tighter together. But the water between them cannot escape fast enough. So pressure builds, and when that pressure gets high enough, the grains lose contact with each other, they separate, they begin to float. The ground does not crack, it does not shift sideways. It does something stranger and worse. It stops being a solid. In seconds, the soil transitions from supporting a load to behaving like a dense liquid. Everything on top of it is no longer supported by solid material. It is sitting on something that flows. That is not a metaphor. It has happened. It has been photographed. There is a photograph from Niigata that stays with you. A complex of 8 4-story apartment buildings, structurally intact, every wall still standing, every window unbroken, tilted past 60 degrees, one overturned entirely. The people inside survived. The building survived. The only thing that failed was the ground they were standing on. They did not collapse. They tilted slowly over the seconds of the earthquake as the soil beneath them stopped behaving like solid earth and started behaving like something else. That image is from 1964. We have been building on liquefiable ground ever since. It happened in Christchurch in 2011, in the Marina district of San Francisco in 1989. In smaller events that do not make international headlines but destroy infrastructure, knock out water systems and cost billions. And the areas at risk are not small. In Tokyo, engineers have identified large zones of liquefiable soil, the same in the Bay Area. In Istanbul, a city of 15 million, sitting on a fault, the maps show entire coastal districts. We know the problem. We have known it for decades. What we have lacked is a solution that scales. The current answer is brute force, and it has a cost most people do not know about. You drill into the ground and inject cement under pressure until it fills every gap between grains and hardens. The The soil becomes low-grade concrete, locked in place, no longer free to move, no longer able to liquefy. It works. But it requires heavy machinery. It cannot easily be done under buildings that are already standing, and the cement industry is one of the largest single sources of industrial carbon emissions on the planet. It is a solution that trades one problem for several others. For decades, researchers have been asking, is there another way? The answer wasn't in a laboratory, it wasn't in an engineering journal. It was in the ground itself, in the rocks that have been sitting there for millions of years. Look at sandstone, look at limestone, look at any sedimentary rock that started as loose particles and became solid. That transformation didn't require a furnace. It didn't require industrial process. It happened through chemistry. Minerals slowly precipitating from solution, crystals forming at the contact points between grains. Over thousands of years, loose material becoming coherent rock. The ground had already solved this problem. It had been solving it since before humans existed. The question researchers started asking wasn't whether it could be done. It already had been done billions of times across geological history. The question was whether it could be done fast enough to matter. The first attempt worked and then failed in a way that made the actual solution obvious. Certain bacteria produce an enzyme called urease. That enzyme catalyzes a reaction that produces calcium carbonate, the same mineral in limestone, the same mineral in chalk. Inject these bacteria into loose soil along with a calcium-rich solution, and as they spread through the ground, they produce urease. The urease drives the reaction, and calcium carbonate precipitates exactly where grains touch, forming mineral bridges. Loose sand becomes something closer to sandstone. In the lab, it worked. Samples showed dramatically improved strength. Resistance to liquefaction improved. For a moment, it felt like the problem had already been solved. Then it left the lab. Left. Bacteria are alive. And alive means unpredictable. They follow the path of least resistance through soil. The easy zones get treated, the harder zones get almost nothing. And in geotechnical engineering, ground that is strong in one place and weak 3 feet away does not give you a foundation. It gives you a new failure mode. So the question became, what if you kept the chemistry but removed the biology? The bacteria were not doing the work themselves. They were producing an enzyme that did the work. What if you skip the bacteria entirely? What if you just inject the enzyme directly? This is enzyme-induced calcite precipitation, EICP. You inject a solution containing 3 ingredients, urease, urea, and calcium. The urease immediately gets to work. It breaks down the urea, splitting it into carbonate ions that disperse through the water between grains. Those ions find the calcium. And when they meet, something happens that has been happening in rock formations for hundreds of millions of years. They crystallize. Not slowly, not over geological time. At the pace of a chemical reaction happening right now underground in the dark between grains of sand you will never see. Zoom in to one of those contact points, 2 grains barely touching, and a gap so small it is measured in microns. The crystals begin forming there first at the point of contact where the geometry focuses the chemistry. Small at first, a few molecules, then a cluster, then something you could almost see under a microscope, a bridge. Then the same thing is happening at the next contact point. And the next, thousands of reactions running in parallel through the treated zone, each one building a connection that was not there before. What was a loose collection of particles, capable of floating, capable of failing, capable of swallowing a building in 30 seconds, becomes a network. Not rigid, not concrete, but held. And the reaction that did all of that proceeded at ambient temperature. No kilns, no furnaces, driven by an enzyme that can be extracted from a common legume without industrial heat. The thing standing between millions of people and catastrophic ground failure is not a missing technology. It is not an unsolved engineering problem. It is a gap between what we already know how to do and what we are actually doing about it. Here is what took researchers a while to fully appreciate and what changes everything about how you think about this problem. When you hear sand turned into stone, the mental image is concrete, something completely solidified, impermeable, rigid. That is not what is happening. More importantly, that is not what is needed. Liquefaction does not require that grains have zero bonds. It requires that enough contacts break so the network can lose coherence. The ground does not need to become rock. It needs to become connected enough that it does not fall apart under stress. And that threshold is lower than you might think. Lab studies have shown that multiple treatment cycles can significantly increase both shear strength and cyclic resistance, the property most directly related to liquefaction behavior. The grains do not need to be cemented into a solid block. They need to be bridged just enough so the network holds when the shaking starts. This is not purely theoretical anymore. Researchers at Arizona State University have already installed field-scale biocemented columns in real sand, using real grouting equipment. The columns were up to 1 meter in diameter and up to 2.5 meters deep. The enzyme was extracted on site from jack beans using nothing more than tap water. No laboratory, no industrial process, no specialized equipment that would not exist on a normal construction site. 3 days after treatment, bearing capacity had tripled, stiffness had tripled. The shear wave velocity, the measurement that tells engineers how a soil will behave in an earthquake, had increased by at least 100 meters per second. 3 days, tap water, a bean, the grains do not float, movement slows, the ground holds, buildings do not tilt, roads do not split, pipes do not rupture. The infrastructure that a city depends on, the water, the power, the roads, the foundations, survives an event that would have destroyed it, not because we made the structures stronger, because we stopped the ground from failing underneath them. So why aren't crews already working in the Marina district? There are 3 reasons, 2 of them are already being solved. The first is distribution. Getting a solution to spread evenly through soil is hard because fluids follow the path of least resistance, which means some zones get treated and others do not. Researchers are working on this with multiple injection points, pressure sequencing and reaction rate management. It is an engineering problem, and engineering problems get solved. The second is BY products. The reaction produces ammonium, which at large scale needs to be managed carefully to protect groundwater. This is also solvable, but it requires planning and monitoring, not just injection and done. The third barrier is time, and this one cannot be engineered away. Civil engineering is slow by design, not because engineers are timid, but because when things built on or in the ground fail, they fail catastrophically. Bridges collapse, foundations give way, people die. The adoption of any new ground improvement method requires not just lab data, but decades of field data. How does the treatment hold up through wet and dry cycles, through freeze and thaw, through sustained load over 20 years, through an actual seismic event? Enzyme-induced calcite precipitation has been under serious investigation for roughly 15 years. Pilot projects are being monitored. The data is accumulating. The bar for trust in critical infrastructure is high, and it should be. That's not a flaw in the technology, that's a timeline. And it's the only thing still standing between this solution and everywhere it needs to be. The same equipment, the same enzyme, the same 3 days. Applied to the coastal zones every city planner quietly writes off, to the districts built on fill that everyone knows will fail, to the ground beneath Tokyo, San Francisco, Istanbul, Jakarta and Mexico City. The people in those cities are still there, the fault lines are still there, the maps showing which ground will fail have not changed. The gap between what this technology can do and where it actually is closing. Not fast enough, but closing. When this scales, the problem that has outlasted every previous solution will not be solved with steel, concrete or machines. It will be solved with an enzyme from a bean.